Happy day, friends. We're here on class 3 here in week 10. So what we're going to do is get a bit of diffraction finished off and get ready for the celebration on Tuesday. So just by way of reminder, PLC 10 is tomorrow. Homework 6, which we have been talking about, we're going to be turning that in Tuesday as well, along with the celebration. So please be ready to go with that, plus celebration too. All right, so based off last class, what I'd like to do is go back and I cooked that example last time, so I kind of want to redo that. Let me go back and do that one with the diffraction grading again, so that it doesn't look like I came up with a sign that was greater than 1. So let's try and do that again. I fixed it up a little bit better this time. And then we'll go through and we'll finish off a little bit more about the resolving power of the diffraction gratings. Alright, so let's assume that we have a diffraction grating which has it has 180 lines, or 180 slits if you like. Per millimeter. And we're going to put light through it, which has, let's say, oh yeah, we were doing the light of wavelength 400, so the light of wavelength 400 nanometers. So we're then going to change this out to a 500 nanometer. And then the question was to try and find what happens, what does the difference in angle look like? So I messed up that grading spacing last time, so let me try and fix that up. So let's start off by finding delta theta between lambda 1 and then lambda 2. Alright, so in this case, we have the operating condition for, and let's do this for the second order. Let's make it a little bit funner this time and look at the second order fringes. So we have our condition for constructive interference in the diffraction grating. Now, we have essentially what we need, and I talked a little bit about this last time as I messed it up, but really what we're doing here is we're going to be looking for the angle, and then I'm going to subtract off the angle. So first thing we need to do is find out what our D is. So I changed it. I had 25,000 per centimeter last time, so now I've got 180 per millimeter this time. That means D looks like a millimeter per 180 slits. And M, we know, is 2. And then when we look at the wavelength, we're going to start with the wavelength at lambda 1 and then put in the wavelength at lambda 2, figure out the angles for both of those, and then make the difference. Alright, we'll do lambda 1 here. Well, the sine of theta 1 then is 2 lambda divided by little d. And that means we're going to do 2 times 400 nanometers. And we're going to divide that by 1 millimeter over 180 in the spacing of d. So I've talked a little bit about this before, but we're going to want to make sure that we get our units copacetic here. So we have the choice of moving these into nanometers or those into millimeters. So let's go ahead and move these into millimeters, I guess. So this is going to then we'll get a unitless angle. So, if we do that, we're going to find the theta 1 arcsine of 800 times 10 to the minus 6, and that's times 180. I got to divide that by, well, 1 millimeter, so I don't have to divide that by anything. Now, if we do that, that's where I got that 8.3 degrees from. That's 8.3 degrees to the second bright fringe for the lambda 1. Right, so for lambda 2, we can do the same thing. And instead of lambda 1 being 400, I'll have lambda 2, which is 500. And that'll lead me to a theta 2, which is 10.4 degrees. And therefore, the difference between these two is 2.1 degrees. Okay. Now, last time I mentioned the dispersion, and so I want to talk a little bit about the dispersion, because the dispersion ability of a grating is its ability to put a large angle between wavelengths. So if we think about, and we also talked about resolution as well, which we can go on. So if I think about the dispersion, just want to take a minute here. The dispersion is essentially, we'll call it capital D, and I don't have a capital D here, do I? No, okay, good. So we call it d theta d lambda. And we came up with an expression for this last time, which was equal to m, the order number, divided by d cos theta. And so, I'm just curious here to see if I think about the dispersion in the sense that I now unlimit this, right? Normally you'd think about taking a limiting procedure to get to a derivative, but what if I now go the opposite way and unlimit this thing? So unlimiting it would put it into the situation where I have delta theta over delta lambda equal to this thing. So what would happen if we just tried to calculate the delta theta using this? Maybe that would be useful. Let's see what happens. Delta theta being m divided by d cos theta, and this thing times delta lambda. Now, I will start this by saying that these two wavelengths that I chose, 400 and 500, are not really close enough together to really qualify for this. You're looking at things that are typically in the tenths, maybe to 1 nanometer difference in wavelengths. So I've got kind of, you can see why I unlimited. This is clearly not, this is not differentially small. It's 100 nanometers, which is enormous. So let's take a look and see, just curious whether this will give us the same type of thing. We used a second order wavelength, second order fringe. So I've got 2, and I've got my D, which is 1 millimeter over 180. Like so. And then the cosine of theta. Well, the theta was kind of between these two. I'm going to start with 8.3. I'm going to see if I can do a cosine of 8.3. And then multiply that by 100 nanometers. But I'm going to have to make sure that I get my 100 nanometers to be 100 times 10 to the minus 6th millimeters in that. I'm just kind of curious whether this is going to work out. So, oops, wrong one. So let's see here. I'm going to do 2 times 180, and I'm going to divide, and I'm going to multiply by 100 times times 10 to the minus 6. Well, that's 10 to the minus 4, so we need to do that. Let's do this back. All right, now let's divide that by the cosine of 8.3, which is what I don't know off the top of my head. At 0.036. 8.3 degrees of negative degrees. Yeah. So I got 0.036. Oops. I did it the wrong way. 0.036. Yeah, not bad. I got 2.06 degrees. Okay, I'm actually a little surprised by that. All right, so I don't feel quite so bad. So this is dispersion. It's the ability of the grating, like I said, to put larger angles between wavelengths. Okay. All right, so there was that part. What was the second part I wanted to do here? We did end up seeing when do they overlap, right? So I wanted to now see, after I found delta theta, I want to now find at what angle do the two fringes overlap. So if you look at this, you'll notice that d sine theta will be the same number if I use the fourth fringe of the 500 and the fifth fringe of the 400. Okay, so that will give me the same angle. What that means is I can calculate the angle at which the two bright fringes should be overlapping, but like I was saying in the last class, it's the fourth fringe for the longer wavelength and the fifth fringe for the shorter one. All right, so these overlap of the lambda 1 m equals 5 fringe with the lambda 2 m equals 4 fringe. All right. Since I have m lambda, then I would say that would be m1 lambda 1, which is 5 times 400 nanometers, or in other words, 2,000 nanometers. That would equal d times sine theta, like so. And I could find that theta. And I can find that theta the same type of way as I did last time. Knowing the new and improved little d, I'd be able to say that sine of theta is m lambda divided by d, and I'm picking number 5 here. So this is 2,000 nanometers divided by 1 millimeter over 180. And that means I have to change my units once again. And then find my theta. So this is going to become 2,000 times 10 to the minus 6 millimeters. And I'm going to multiply that by 180. And so when I do find the theta that's common to both of them, it is 21 degrees. 21.1 degrees. Okay. All right, last piece that I did was to calculate how many total fringes do we see. So let's assume that we have let's assume that we're looking at the lambda 2 wavelength here. Right, so the question is, how many fringes does lambda 2 produce? That's in total. Okay. The largest possible angle that you can have for this situation, I think this is the same thing as I showed you before, is that when the light comes out of these, when the light comes out of these slits, right, we can draw the rays as perpendicular to the wavefronts. Okay, but we have to realize that they're going to spread, right, like this, and the largest possible angle I'm going to get from that is going to be the one in which it goes directly parallel with the actual grating itself. Right? So it's either going straight down or straight up, and that's going to correspond to an angle of 90 degrees. You're not going to see any fringes past 90 degrees, because that means like the light's reflecting off the grating rather than going through it, so that would change things a little bit. But nonetheless, we're going to say at an angle of 90 degrees, we get the maximum, we'll be able to solve for the maximum number of fringes. So that means I can calculate M by saying, if I take this thing here, I'm just going to swing the wavelength underneath. I'm going to have d over lambda out front, and then my sine of 90 degrees, which is going to be pretty nice. Oops, d over lambda. Started off badly right here. D divided by lambda, but my sine of 90 degrees, right? That's just 1. And so this is the maximum number of fringes that I'm going to be seeing on the screen. And in this case, if I do this number with 500, suppose I take lambda 2 here, I do 1 millimeter over 180 divided by 500 nanometers, which I'll just change to 500 times 10 to the minus 6 millimeters. Right? If I calculate that number, it turns into 11. Just make sure I get this one. So this is 5. This is what? 1 divided by 500 divided by 180. Yeah, so it turns into 11, but that's the biggest integer. It's 11.1. But the 0.1 means we've already passed the 11th bright fringe, and we're already, if you think the relationship to double slit interference, right? We're already past the 11th maximum, and we're going down into the, I guess it would be the 12th minimum, or maybe it's the 11th. Well, whatever it is. We'd be going into the next minimum. We've already passed the maximum. So that's the biggest integer, and so that's the largest number of fringes we'd see, or at least we might be able to detect from this particular grating at that wavelength. Now, if I wanted the 400s, I'd just put 400 in here, and I'd get probably, I don't know, 13 or 14 out of this. So that's that, okay? Okay, so hopefully checked that box of making the example work a little bit better. I want to go back and revisit a little bit more on dispersion and resolution, so that we have a better understanding. Oh, and I messed something up on resolution last time, I realized. So let's talk about that too. So I showed you just here how to calculate the dispersion, or how to use the dispersion thing to calculate angle differences. I'll do another example with slightly closer spaced wavelengths in just a minute, but I wanted to talk a little bit about dispersion versus resolution. These are two qualities of the diffraction grating, both of which work to separate wavelengths from each other. Okay? So dispersion has to do with the angle. Right? This is all about what angle we're going to be getting. Now, if you're thinking about why does a diffraction grating give you an angle of the wavelength, it's because of the number of slits. Right? It's not the number, it's really the slit spacing. Right? So this has to do with little d. That means the more slits I can jam into a given distance, right, or the lower I can make this number, the better the angle's going to be. Okay, because what that means is for a given order number and a given wavelength, the right side of this stays constant if I'm looking at a particular order number, right? But if I'm shrinking the distance between the slits, then that order number is getting pushed out more. My sine of theta is increasing. Okay? So for this being constant, then I can make differences if I drop the little d, I'm going to increase the angle. And that's what the dispersion's about. It's about dispersing the light, like getting it out to different angles. Okay? The resolution is essentially about the peak or the widths of the bright fringes of the maximum. So this is basically bright fringe width. Well, we only have bright fringes in the diffraction grating, so bright doesn't really matter. Width. Okay. So the bright fringe width. Then this was something I got backwards in the class yesterday. So let me go through and figure that one out. We had the resolution. I think I said it was delta lambda over lambda. Which would be, and then I said that was equal to n times m, but that's not quite right. It should be 1 over n times m. Where m is still your typical order number. Right? That's my fringe number. Just like it was back here, same m. But capital N is the number of slits that you've illuminated with the light. Okay? It's not the total number of slits in the grating. It's not the number of slits per distance. It's just the number of slits that the light that you're putting through is illuminating. So if you look at the laser that I had last time, it had a small spot to it, right? And then I had a grating that was probably about that size. So then you'd say, well, I had something like 15,000 slits in that grating, and the laser line was probably illuminating somewhere in the range of about 2,000 of them. For some, it looked like it was about an eighth worth, so it's probably a little more than 2,000. But nonetheless, so make that correction, please. That's a 1 over. And then I also want to talk a little bit about what this wavelength is, because ultimately, what the resolution is trying to do is it's trying to, in a Rayleigh criterion sort of way, it's trying to say how close can these two wavelengths be such that we can distinguish their fringes. Okay, so it's got to do with the peak widths, right? The fringe widths. Now, what this is predicated on is I have two wavelengths, so which one am I using in the bottom part of this? Well, it turns out you might as well just use the average because it's pretty close to either one of them. All right, we're going to take two wavelengths. We're going to have lambda 1, and then we're going to have lambda 2, which is equal to lambda 1 plus a little bit. Really close together, and what we want to do is see if there's actually two lines. Can the diffraction grating resolve these two lines? So here what we're going to do is we're going to use the average wavelength for this thing here, right? So that's going to be 1/2 of lambda 1 plus lambda 2. Okay. I want to give you an example of what good and not so good dispersion and resolution mean when you look at the light that comes out of the diffraction grating. All right. So suppose that I have a situation where well, let's start with the best possible thing here. Let's suppose I look at good dispersion and good resolution. Let's suppose that I look at good dispersion and good resolution, good DNR. That means that when I look at the intensities of these things, okay, so suppose that I'm going to draw here a screen. Instead of having it vertical, I'm going to have it horizontal. And we're going to look at the intensities on the screen of the signals produced by the wavelengths through the grating. Now, if I have good dispersion and resolution, let's suppose that my central maximum is over here, and I'm only going to draw on the one side here. So let's suppose that my central maximum is over here. Remember, the central maximum is the place where all the light that you saw, that you can see with your eye, goes straight through, and it doesn't look any different. So if you have white light coming through, it's going to be a white spot in the central maximum. And then after that, you're going to start seeing, oh, look, there's a blue, green, yellow, right? And you're going to see the colors that make up that light. But the central maximum is everything all mixed together, so you have no ability to determine anything from the central maximum. So good dispersion and good resolution means that I've got a good angle. It's about right. Remember, I'm going to deal with these two wavelengths. They're really closely spaced together, and I want to see if I've got good dispersion. What does that mean? That means I've got a good angle away, right? So I'm going to have a good amount of angular distance between the two wavelengths. And then my resolution means I'm going to have a really thin peak for both of them. So what that means is I'm going to look at something that looks like this. And I'm going to look at something like that. That's good dispersion, right? These things have a good angle between them. Their peaks are really narrow. This is good dispersion and good resolution. And you can go from here. Suppose that I have good dispersion, but poor resolution. In other words, I'm getting a good angle between these things. But unfortunately, the resolution is not enough such that my peak width, let me draw it down here. My peak widths now look like this. Right? I'm getting significant overlap between these two peaks. This is good dispersion because the angles are still good, but bad resolution because my peak widths are so large. Let's look at a case now where I have good resolution, but poor dispersion. Again, I'm going to go with the same idea here. Central maximum is over here. Now I have good dispersion. No, I have bad dispersion and I have good resolution. So my peaks are going to be really, thin, right? Which is going to be great. But unfortunately, they're basically right on top of each other. So I'm not getting a very good angle between these two. My dispersion is lacking, okay? Now, of course, if I have bad dispersion and bad resolution, you can see what's gonna happen. I'm gonna take these two bad resolution peak widths and put them on top of the bad dispersion angle bit here. So you're gonna get two big long peaks like this, so you can see that one happening, okay? That's the difference between dispersion and resolution, okay? It's where, dispersion is how much angle am I talking about, and resolution is how thin is the peak, or how thick, if you like. If it's good resolution, it's a nice thin peak. So I just cooked up an example on this. Now sodium exactly matches this type of thinking. Right? Sodium has a very famous what's called doublet. In other words, there's a line that you can look at in sodium, and it's kind of a thick yellow line. But if you put it through a grating which has good dispersion and good resolution, you suddenly find that there's actually two yellow wavelengths there. They are different wavelengths, and with a good grating, you can distinguish between the two. Okay, with a normal grating, like the one I brought in yesterday, it would be something probably like this. I would not have very good resolution on that grating, but the dispersion would be reasonable, okay? So sodium has a very famous doublet line at lambda 1 being 589 nanometers, nanometers, and lambda 2 being 589, 0.59 nanometers. Okay, so the question is, what kind of grating would we need in order to resolve these two wavelengths? So let's do two things. Let's start by supposing I have a grating with a known slit separation, and then we'll try to calculate the angles that go on here. So what kind of angle do I have? And then let's go through and say, okay, what kind of resolution would I need in my grating in order to resolve these two lines and get it into a situation that looks like this? All right, so let's suppose that we take, a grating. So this is the sodium example. Let's suppose we take a grating that has 12,600 slits per inch. Per inch means 25.4 millimeters. Okay, that's pretty close to the grating I had yesterday. I think I have 15,000 in that one. So this is basically the same type of grating. All right, so what I want to do to start with here is to find the angle at which this line is going to show up. Okay, so I'm going to look at the first order. I'm going to look at that wavelength with this slit spacing, and we're going to find out what angle, just exactly like we did with the other one. Okay, so let's start by finding theta for the 589. And ultimately, I'm not going to worry too much about using 589 or 589.59 because they're basically the same thing when it comes to this type of thing. So let's start by setting up the sine theta. That's going to be m lambda divided by little d. I'm going to look at the first order, so I'm going to set m equal to 1. We're going to use 589, and then we're going to look at little d being calculable from this thing, which I went ahead and calculated this time instead of leaving it as a fraction. If you do that, if you do this, and you change it, I changed it into nanometers to make life a little simpler. This is a little over 2,000 nanometers. Okay, instead of leaving it as a fraction. We can go in and calculate this here for the first order, so that's going to be 1 times 589 divided by 2016. All right, that's going to give me a theta. I calculated that theta at 17 degrees. Just a smidge under, but basically rounded to 17. Okay, now that I have the slit spacing and the angle, I can calculate with that, because remember, the dispersion of the grating depends on the slit spacing, okay, and that's what produces the angle. So let's look at what dispersion this grating is going to be able to provide for me, and therefore what delta theta am I expecting in the angular difference between the first order bright fringes between these two. All right, so if I look at dispersion, and I want to calculate the angle between these two, I'm going to use d times delta lambda. Okay, so just in the same way that I unlimited the dispersion last time into becoming a delta rather than differentially small things, I'm going to do the same thing here. We're going to come up with a delta theta. Our delta lambda, we know it's about 0.6 nanometers, and I now have to calculate what the dispersion of this is. Okay. So the dispersion of this particular grating at the first order, we know we have this. We know we have this going on for the dispersion. So for our purposes, all I'm going to have to do is multiply this fraction by the difference here, which is 0.6 nanometers, and then I'll have what the difference in the angle is going to be in the first order between these two. All right, so if I do 1 divided by little d, which is 2016 nanometers, and I do the cosine of 17 degrees, right? I'm going to take that number and multiply by the delta lambda here. Okay, so I'm going to do d multiplying 0.6 nanometers. And when I roll through all of that, what you're going to get is a number in radians. Okay? You're going to get out a number in radians. I changed it into degrees just to take a look, but make no mistake, this delta theta is coming out in radians. So this is going to look like 0.0175 degrees. Okay, so a couple hundredths of a degree. That is seeable with a pretty good spectroscope, as long as you have a nice fine adjustment on the vernier scale on a spectroscope. I'm pretty sure we have one of those in the lab here that could see that. Okay, so as you'd expect, that's a pretty small spacing. That's not like 20 degrees or 2 degrees or whatever like I had with the other one, where we were talking about a difference in 100 nanometers. Yeah, it was 2 degrees between the two, right? When I had the 400 and the 500, it was 2 degrees between their second orders. Well, this is a lot less than 100 nanometers, so naturally this angle is going to be a lot less. And also note that when I did this calculation for that situation, I did actually have to convert that from radians and degrees to get the 2 degrees. So note that. Now the question might come into, all right, how many slits do I need to illuminate in order to resolve these two peaks. Okay, so this kind of goes back to the Rayleigh criterion, whereby we said, look, if we're gonna have a diffraction pattern and you're gonna try to distinguish between two sources, okay, then you have to at least have one of the maxima be in the minimum of the other one. That's the bare minimum to being able to distinguish between the two sources. And that's how the resolution basically comes about and gets calculated. And I'm not really going to go into that too much as to how this comes about, but essentially delta lambda over lambda is equal to 1 divided by number of slits times the order number. Now remember, this is the number of illuminated slits, not the total number of slits. So the question is, how many, if I have a grating that has 12,600 lines per inch, then how many of these do I have to illuminate before I can distinguish between these two peaks? So in order to make that happen, what I'm going to do is solve for n. And if you do that, you're going to chuck that up here, you're going to pop those things down there. So I'm going to lambda divided by m times delta lambda. And this is going to tell us the minimum number of slits necessary in order that I get one maximum peak that's positioned directly on the minimum, the first diffraction minimum of the other peak. So here in this case, now remember I have to use the average lambda for this. So I'm going to take halfway between these two, so I'll just call it a 0.3 in the middle here. I'm going to take 589.3 and I'm going to divide by m, but we were only looking at the first order, and so I'm going to then look at the delta, which I'm going to say is 0.6, and that's nanometers also. So my nanometers go away, and so my number of slits is basically going to be 1,000. Right, so this is a number about 1,000. Right? This number should come out unitless because it's all it is counting the number of slits that you've illuminated with the light. All right. Okay. So that gives the resolution and the dispersion for gratings and how to use them. So what that means is I think we've come to about the end of the wave optics section, which is pretty good timing. That means celebration 2 is on Tuesday, and we can talk about things to expect and mentalities to bring in. I mentioned in the last class that the mechanism of the celebration will be the same. Okay, in other words, there will be likely pretty much the same number of problems, which I think is 5 problems plus a conceptual, and the same time. And what else? You have the day, you do the usual, right? Make sure you've got yourself squared away with good internet and that you're not freaking out, okay? Because as soon as you start freaking out, then things tend to get worse. So try not to freak out. Make sure you're all set up well. Celebration 2, the topics. Everything since the since the first one. So this is geometric optics. And that's going to include, so reflection and refraction. We started off talking about just the behavior of light waves, okay?
what's going to be useful here is for you to be able to draw reasonably good beams, rays, right? Such that you can communicate to me what your understanding of the reflection and or refraction is. So in terms of general mentalities, remember that you're trying to communicate things to me. So if there are things that you know that you're not putting in, then I don't know that you know these things, okay? I can only go by what I am reading on the paper or reading on the screen or however it is that you did this. So I highly recommend that increasing the amount of communication. If you can draw a picture that's gonna help convey your understanding, I would suggest you do that. And for the most part, that's really kind of also what I'm expecting to see. So it's going to be very useful for me to understand your intuition on the problem by looking at what diagram you've drawn, okay? And then how do you mathematically represent that diagram? So making sure that the diagram conveys what you want it to convey, and that your mathematics then shows what your diagram is telling me, okay? That consistency is definitely something I keep an eye on. So for example, if we're talking about refraction and then all of a sudden you're talking about light beams bouncing off the tops of surfaces and things like this thing, well, you're mixing up refraction and reflection, then I'm concerned that you're not quite understanding what's going on, okay? The other part to this is, of course, read the problem carefully and check back in on it. I know that I probably read the problem statements upwards of 3 to 5 times just to go back to even if someone asks me a homework question, okay, I'm gonna read the thing, kind of start setting it up, I'm gonna go back and read it again. What are we doing here? Oh yeah. Oh wait, what do I want? Oh yeah. So I am obviously old and decrepit and therefore senile, so I don't remember these things, but I feel that in the first celebration and some other parts of things that the reading to understand part of things hasn't quite been there. So for some of you, just making sure that you're reading the problem, because it's not that fun for me if I kind of feel like, gosh, I think you know what you're doing, but you instead of answering this question, you answered that one. I can't help you out that much, okay? So try to give me something that I can work with. All right, back to this. We talked about reflection and refraction. We talked about Snell's law here. Snell's law is one of those things that's really easy to write down, but then if you have to use it multiple times, it's very easy to mix up, or / very easy for someone reading your work to mix up what you're doing. So try to make it obvious as to how you're applying Snell's law to things. That does include both refraction in and out of different index materials, as well as total internal reflection, and the conditions for that as well. So that's part of all of this. And then once we got away from basics of these two, we went into mirrors and lenses and found that the basics of how to operate with these was the same. The mirror equation and the thin lens equation were the same. The sign conventions worked out the same if you thought about what light kind of was supposed to be doing to make an image and that type of thing. All right, so pay attention to sign conventions and things like that. I I will say that, oh, and then of course we had Fermat's principle. The principle of least time. I will say that you're probably not having any mathematical trouble in this class. In other words, the associated mathematical representations for these are just basically algebraic, right? We have done very little actual calculus in this class. So mathematically, it's probably not very challenging. However, it's easy to get very quickly and destructively derailed by messing up signs, okay? So make sure your algebra signs are telling you what you want. When you're dealing with mirrors and lenses, certainly be able to draw the ray diagrams. You should probably check in on the principal rays that we talked about, how to draw those, what are their behaviors, how the lens thickness makes the ray diagram easier to deal with, et cetera, as well as the algebraic signs, the sign conventions of these two things. Pay attention to that. In terms of geometric optics, I don't think there was anything other than those. Yeah, just like I said, ray diagrams, being able to draw the ray diagrams and then making your calculations copacetic with the diagrams, that's a thing to think about. Same thing with the ray travel through materials or bouncing off if it's internal reflection, making sure that the rays that you're drawing are doing what they should be doing, right? They're bending away from the normal if you're going to an index that's lower, or towards if it's higher, or if bouncing off if it's the critical angle, etc., right? So making sure that the picture that you're giving me matches your math. All right, and then I think we moved into wave optics. Geometric, I should also probably put ray optics up here so that they're titled appropriately. So now we went to the situation and know the different, like macro stuff, right? What's the difference between these two things? Why do we need this and this? Why can't we just get by with that? What's this introducing? What's the new thing, right? So thinking about large scale things about physically, what's the difference in these models? We talked about the three types of ways to get waves to interfere. In other words, how do you produce a phase shift between waves? Let me put it that way, three ways to produce a phase shift. Right, and we concentrated basically on two waves for most of the beginning part of this. We started with the wavelength reductions, okay? And we looked at how many waves fit into a particular length by counting the wavelength ratio to the length of the travel. And then we looked at where do they come out? What kind of interference is going to be produced by these waves? Interpreting the phase shift between the waves means we can tell what type of interference is now going to happen. So interpreting that phase shift means you're either doing it from the wavelength point of view or from the phase, like the radians point of view, okay? we've used both of those situations, okay? We have not particularly used the phase of the wave in a mathematical sense, but we've talked about the relative phases between waves, both in terms of how many wavelengths off are they, or how many radians off are they, or degrees if you like, okay? So interpreting the phase shift between the two waves to give the constructive, destructive, or partial interference between the two waves and interpreting that. We moved into the two-slit experiment. In which we use this to focus mainly on the path length difference, okay? So that was the second way to produce interference. We have the wavelength reduction, the path length difference, and that was what we used to show the two-slit was what we used to show the path length difference. And then we got into the third type of interference, which is the thin film interference, which, the reflection interference, which is part of thin film interference. Okay. Thin film interference actually uses all three of these. And so being able to understand the reflection phase shifts and the path length differences and the wavelength reductions, and then setting all that up is going to be how you need to attack the thin film problems, okay? Once again, a drawing of the two interfering waves, what's happening with the reflection phase shifts, how are you setting up the path length differences and the wavelength reductions, all right? Making sure that you have a setup. I would say probably 70 to 80, sometimes even 90% of the problem is contained within the setup of it. That means a drawing which is clear and shows the behavior that you're looking for, and then appropriately consistent mathematical representation of the picture drawing that you've made. Once you get to there, and then you say, well, I need to solve for theta or something like this, right? Then you can just show how to do that, right? Most of the work that you're putting into the problems is in the setup. So make sure your setups are leading me in the way you want to lead me. Sometimes this means that you have to look back at the problem as if you have never seen it before, even though you wrote it, and go, what did I mean here? Oh, that doesn't make sense. Make it so this, write this over here, right? So thinking about how you're communicating that. We went to two-slit setup for path length difference. We did thin film interference with all three. On top of all of this, we've done the single slit, right? And this is known as diffraction, but really is just interference of many waves. In these two cases, we're talking about interference of only two waves. So the mental expenditure is not so great. But once you start dealing with many waves, it starts to become a little bit harder to keep track of the interference. So it's called diffraction, but we know it's really just interference between many waves. Understanding how the single slit pattern and the double slit pattern mesh together. The intensities, okay? The locations of the fringes, the small angle approximations. What are we seeing on the screen? Whereabouts are they? Thinking through all of this, okay? Knowing how to keep these separate from one another. Yet, when you need to, put them together by multiplying the intensities or some such, okay? Or checking where does the diffraction minimum intersect the interference pattern? Is it at a maximum? Is it a minimum? Is it in between? Where are these two patterns lining up? Okay, putting those together. I feel like that's a place where you definitely want to make sure that you are pretty solid. And knowing the differences in the conditions, right? We have the two-slit experiment, which gives us maximum and minimum conditions. We have the single slit experiment, which gives us the minimum conditions. We have thin films, which does who knows what. We have to actually set it up in order to figure out what we've got. Lastly, in here, the diffraction grating and the resolution of objects. Resolution. So the resolution of objects via the Rayleigh criterion, as in the headlight problem in the homework, and diffraction gratings as we've just been going through yesterday and today. As far as I can see, those are it. Making sure that you are, I just am repeating myself here. So making sure that you're communicating the things you want to communicate and being consistent with how you're communicating it. All right. In terms of that, I don't think I have anything else to say. In terms of mechanics of the thing, I don't think I have anything else to say. I do prefer it if when you do your celebration, you do one problem per page. It can be front or back, but it's a lot tougher to keep track of if you have numbers 2, 3, and 4 on the same page. If you don't mind, just do number 2 on one side, number 3 on the other side, number 3, right? And just start a fresh page with the problems, and that helps with how I'm going through things. Other than that, I don't think I have anything else. So I'm going to be saying that I can call this done for now. We will not have class on Tuesday. The celebration will be posted and available throughout the day. But of course, midnight is the time. Well, actually, it's 11:59 is the time, because this is a computer and it does not round the way I round. So 11:59 is the time, and please be sure that you are on top of all of the things you need to be on top of in order to make the submitting of things and all of that stuff go smoothly. Okay? If you need to practice photoing or PDFing your stuff so that it's a nice, easy process, I'd suggest you make that into something that you're feeling really comfortable with. All right? All right. So to that end, I will then say good luck, and I will get to the lab posting that will show up tomorrow. But since you do have a celebration on the Tuesday, we're going to push off the lab write-up due until Thursday of the next week. Okay, so just to make sure you're aware of that, the lab will still post on Friday of this week, but the due date will be Thursday of next week rather than Tuesday. All right? Okay, so that's what I got for you. Good luck, and we will see you we'll see you tomorrow, but we'll see you in class next week on Wednesday for 2 classes. All righty, happy weekend and be strong.